Number 7, again, we're doing a hypothesis test for the difference population mean. We're going to do the t-test on this one again, if I could get this to stop where I wanted it to. And so, it says the University Data Center has 2 main computers. The center wants to examine whether computer 1 is receiving tasks which require comparable processing times to those of computer 2. A random sample of 15 processing times from computer 1. So n is going to be 15. Show a mean of 38 seconds. So x bar is 38 seconds with a standard deviation of 15 seconds. So my standard deviation, S1, is going to be 15. I should put ones there since we have 2 different things we're surveying. Then we're going to do computer 2. So a random sample of 10 processing times from computer 2. N2 is going to be 10. Show a mean of 51 seconds. So x bar 2 is 51 with a standard deviation of 19. S2 is 19. Assume that the populations of processing times are normally distributed for each of the 2 computers and that the variances are equal. Can we conclude that at a 0.1 levels of significance that the mean processing time of computer 1 is less than the mean processing time of computer 2? So if I'm going to say that U1 is less than U2, would that be my null or my alternative hypothesis? That's my alternative one, right? Now they're going to do something weird on this because they like to compare it to 0 like we were doing on the previous problem. So what they're going to end up doing is taking this and moving it over here. So they're going to say the mean of 1 minus the mean of 2 is less than 0. Here then, the mean of 1 minus the mean of 2 would be greater than or equal to 0. All right, so now this is going back to the formula that we started with way back on homework 18, where we first have to find our SP number. The SP number again was N1 minus 1 times S1 squared plus N2 minus 1 times S2 squared over my degree of freedom. My degree of freedom again, when we did our degree of freedom, was the N1 plus the N2 minus 2. This was from homework 18, problem 6, 7, and 8, or somewhere in there. That's the first part of our formula. So when I find SP, N1 is 15. So I'm going to have 15 minus 1 times my standard deviation squared. So my standard deviation is 15, so 15 squared. I got too many 15s in this problem. Plus N2 was 10. So 10 minus 1 times my standard deviation is 19. So 19 squared, if I sneak that in behind there. And then my degree of freedom is going to be N1 plus N2, so 15 plus 10 minus 2. That would be 25 minus 2, which I'm just going to go ahead and calculate as 23 then, right? So first thing we have to do is figure out what SP is. We are going to carry that out to 3 decimal places. Intermediate calculations to 3 decimal places.
What's that say right there? 19
Squared.
squared.
That was my S2 squared that I didn't have room to write, so I tried to smush it in there. So, yes, that was 19 squared. So if you figure out that number, what do we get? And if you wanted to make this so you could type it in faster, you could just do this calculation and do 14 times 15 squared and 9 times 19 squared divided by your 23. And then you don't have to put all the parentheses and stuff in there, right? What did we get when we figured out that value? $278.217. Okay, so same formula we used on homework 18. Now we have to figure out the test statistic, which I skipped over that. We better put that in there. We're doing a t-test with a degree of freedom of 23. That was the bottom number here. So now for my formula, I'm going to do the mean of the first one minus the mean of the second one over, and then I'm going to have the square root of the SP times 1 over N1 plus 1 over N2. So it looks like a lot like the confidence interval formula, except for you're dividing instead of subtracting. So, mean of the first one would be 38, minus the mean of the second one, which was 51, over the square root of the number we got over here, 278.217, times 1 over N1, which is 15, plus 1 over N2, which is 10. Again, all that goes under the square root when you type that in. So make sure as you go to the next part, you click right behind whatever you have there. And again, we're going to round this to 3 decimal places. Negative 1.909. Okay. So on this one here, when we think about our test, we are doing just the one-tailed test. Since the alternative hypothesis is a less than, we're doing the less than. When we do the critical value, we would end up getting the positive number, which would be the right-tailed test. So when we do it, we're going to use negative the value. So you're going to do T sub 0.1 with the degree of freedom of 23, but instead of using the positive answer, you're going to use the negative answer because you're doing a left-tailed test instead of a right-tailed test. Right? Just like when we do our one with the 2 sides, we have both a plus and a minus. We want the minus end of our graph. So if you do your degree or your T sub 0.1 level of significance, since it's just a one-tailed test with a degree of freedom of 23, you get 1.319. Since we know we're on the left end, we're going to use negative 1.319. Okay? We then are going to test that out. So again, this section with the less than is our alternative hypothesis. The other side would be our null hypothesis. We're trying to figure out in which side does negative 1.909 fall. Is it on the left or is it on the right of that critical value? It's on the left side, right? This is smaller than this is, so my negative 1.909 would fall in that section there on the left side. That means that my alternative hypothesis is the true one, the null is the one that's not true. So, can we conclude that the mean processing time of computer 1 is less than the mean processing time of computer 2? Yes, we can. The true statement was that it was less, right? So can we conclude that it's less? Yes, we can. All right, number 8. Basically this, whoa, the same kind of thing here, but we've got our lifetime of light bulbs in hours in a table. So again on this one, because we need the mean and we need the standard deviation, we're just going to use our calculator and do list 1 and list 2 and find those calculations. So you two in the front want to do list 1 and you two in the back want to do list 2? It says a purchasing manager for a large university is investigating which brand of LCD projectors to purchase to equip a smart classroom. Of major concern is the longevity of the light bulbs used in the projectors. The purchasing managers have narrowed down the choices of projector to 2 brands, InFocus or Proxima, and wishes to determine if there is any difference between the 2 brands in the mean lifetimes of the bulbs. The purchasing manager obtained 8 projectors of each brand. So we know we have 8 there. The number of hours the bulbs lasted in each of the 8 machines are given in my table. Assume the 2 populations of lifetimes are normally distributed and that the populations variances are equal. Can we conclude at the 0.01 level of significance that there is a difference in the mean lifetimes? So in here again, we're going to say mean 1 minus mean 2, mean 1 minus mean 2. And the question wants to know, is there a difference? When it asks, is there a difference? My null is going to say, it's equal to 0. My alternative one, not equal to 0. So is there a difference? I'm going to subtract. If there's no difference, it would be equal to 0. If there is a difference, not equal to 0. So hopefully you've got some of that typed in there. My mean of my first set of data. So the mean of this set of data here. Did you guys get that into list 1?
Oh.
And then, yep, stat, calculate your 1 variable statistics.
Which one did first?
The X bar, the mean.
43.375.
375. My standard deviation, the S1 of that list of data.
80.096.
Yep. And the N, how many numbers did we have on that list? We had 8, right?
Yeah.
On my second list of data, so on my bottom list of data, the mean of the second list was 775.375. My standard deviation for my second set of data is 101.410, and my number of values was 8 again, right? All right, degree of freedom, I'm going to do that right away. For my degree of freedom, we did n1 plus n2 minus 2. So in this case, we have 8 plus 8 minus 2. 16 minus 2 gives us 14 degree of freedom. So over here, what type of test? We're doing the t-test with the degree of freedom of 14. I'm not leaving myself much writing room. I have to do my first formula. My first formula for my SP. We did n1 minus 1, so 8 minus 1, times the standard deviation squared, so 80.096 squared, plus n2 minus 1, so again we have 8 minus 1, times our standard deviation squared, 101.410. You can almost read my 4. That was squared. That is all over the degree of freedom, which is your 14. I'm just going to put DF there for the degree of freedom. So if we calculate that SP value and round that to 3 decimal places, what are we coming up with? 8,349.679. We used that when we did the second part of our formula. The second part of our formula, we did x bar of 1 minus x bar of 2 divided by the square root of that SP value times 1 over n1 plus 1 over n2. So our x bar from 1, 843.375 minus the x bar from 2, 775.375 over the square root of that answer we got there, 8349.679 times 1 over n1, which is 8, plus 1 over n2, which is also 8. $1.488. 1.488. All right. We are going to find the p-value on this one. So we are going to do the P of T is greater than 1.488 with a degree of freedom of 14. The p-value is the percentage that's in that section. Again, I'm going to draw my little table here because we were doing a two-tailed test. So when you do P of T is greater than 1.488 with a degree of freedom of 14, you get okay, we get 0.079. Now that's the percent that's in this section. We're doing a two-tailed test. So that means the percent that's in this other section is also 0.079. So in order to find our total percentage, we either have to add those together or multiply by 2 since they're the same number, right? Kind of remember doing that last week when we did the t-test and we had a two-tailed test? When we do the p-value, if I'm doing the two-tailed test, I end up multiplying it by 2 since I'm doing both ends. The percent on this end is 7.9, the percent on this end is 7.9, so if we add them together, we get
These are add.
yep, or multiply by 2, either way, it's the same thing, right?
0.158.
0.158. So that means we have a 15.8% confidence that we have the thing correct. We want to test it at a 0.01 level. So 0.158. Is that greater than or less than 0.01? It is greater than. And if my p-value is greater than my level of significance, we are going to do what? Accept the null. We're going to say this is our true statement, then that one is not true. We're saying it is equal, right? So, can we conclude that there is a difference in the mean lifetimes? Can we say there's a difference? No, we're saying it's equal. There is not a difference. I didn't leave space for the no, but on the bottom one, you're going to circle no. We're saying they're the same. They're not different. Okay? Number 9, same kind of thing. Good, they gave us all the data. We don't have to figure it out. So, the University Data Center has 2 main computers. The center wants to examine whether computer 1 is receiving tasks which require comparable processing times to those of computer 2. A random sample of 15 processing times, N1 is 15, from computer 1 showed a mean of 58 seconds, so X bar 1 is 58 seconds, with a standard deviation of 20 seconds, so S1 is 20. While a random sample of 10 processing times from computer 2, so N2 is 10, showed a mean of 53 seconds with a standard deviation of 16 seconds. So X bar 2 is 53 seconds, standard deviation 2 was 16 seconds. Assume the populations of processing times are normally distributed for each of the 2 computers and that the variances are equal. Can we conclude at a 0.5 level of significance that the mean processing time of computer 1 is greater than the mean processing time of computer 2? So we want the mean of 1 to be greater than the mean of 2. Of course, they're going to rearrange those. The greater than would be which one, the null or the alternative hypothesis? the alternative. It doesn't have an equal sign in it, right? So we're going to rearrange this and say the mean of 1 minus the mean of 2 is greater than 0, which means this one is the mean of 1 minus the mean of 2 is less than or equal to 0, right? The null always has the equal to in it, which means on this one we're doing a right-tailed test. As long as I'm figuring it out, I'm doing the greater. All right, the type of test statistic, we know that it's a t-test. We have to find the degree of freedom. How are we going to find the degree of freedom? 15 plus 10 minus 2. N1 plus N2 minus 2. 25 minus 2 is 23. Oops, degree of freedom of 23. All right. We then have to find the value of our test statistic, but first of all, before we can do that, we have to find SP. SP. I'm going to take N1 minus 1 times the standard deviation squared. So 15 minus 1 times 20 squared plus N2 minus 1 times the standard deviation squared. So 10 minus 1 times 16 squared, all over the degree of freedom, that 23 that we had. To 3 decimal places we get 652. 343.652. Now we can find the value of our test statistic by taking the mean of the first minus the mean of the second over the square root of that SP value times 1 over N1 plus 1 over N2. So the mean of the first, 58, minus the mean of the second, 53, over the square root of our lovely number we got there, 343.652 times 1 over N1, which was 15, plus 1 over N2, which is 10. So 58 minus 53, subtracting my means over the square root of SP, which is our number we found here, times 1 over N1 plus 1 over N2. So 1/15 plus 1/10. And again, we're rounding to 3 decimal places. Yep. 0.661 is what you should be coming up with. We are doing the critical value. We are doing a right-tailed test. So on our critical value, we're going to do T sub. Since it's just a one-tailed test, we use that number, 0.05 with a degree of freedom of 23. Since I'm going to the right, I should get my positive number. If I was going to the left, I'd have to use the negative, but we're going to get the positive. So when you punch that in, your critical value is going to be 1.714. So 1.714 is my cutoff between the two sections. The greater than section is your alternative hypothesis. That's your H1, which means the less than or equal to on the left side is your null. Does your test value, the 0.661, fall on the left or on the right of that critical value? It falls on the left. We know that the 0.661 is in that section. That means that my null statement is the one that's true. That means my alternative one is not true. So, can we conclude that the mean processing times of computer 1 is greater than computer 2? Can we say computer 1 is greater than computer 2? I think I heard somebody whisper.
Oh, no, you can't.
No, we can't. That is not true. We're saying that's the not true statement, the one with the greater than. So, no, we can't conclude that. It's not true.